The standard textbook model of vision is highly linear. Photons enter the eye, strike the retinal cones, and trigger a sequential chain of electrical spikes that march straight into the visual cortex. It is an intuitive, feed-forward heuristic. But there is a specific biological state where this model completely breaks down. We observe it every night during REM sleep. During deep dream cycles, the brain renders intensely saturated, fully stable visual scenes. It constructs rich reds and deep blues in pitch-black rooms, completely void of any external photons, between 400 and 700 nanometers. To account for vision without light, we have to look past the idea of the brain as a passive camera. The topological approach of the Brain Kinematics Model offers a different mechanism. In this framework, color is not a direct translation of a physical wavelength. It is a metastable, multi-layer strain geometry, a structural balance struck between competing neural networks. Because the sleeping brain builds color from pure neural equilibrium, we can identify waking vision as a process of active internal stabilization. The assumption that color is an isolated property of the external world goes back to the origins of classical optics, which defined it strictly by external wavelength. When Isaac Newton decomposed white light, he established that objects selectively absorb and reflect specific bands of the spectrum. He took those spectral bands and mapped them into a circular arrangement. This was an early attempt to organize perception into a formal geometry. Over the centuries, our advancing technology demanded standardization. We built strict coordinate spaces to mathematically codify human color matching. This chart shows the CIE XYZ system. It maps physical wavelength limits into a standardized three-dimensional perceptual space. But treating this as a complete reflection of the brain reveals a critical flaw. The boundary lines here are rigid. The coordinates are fixed. Human perception constantly shifts. Opposing neural channels balance red against green, while memory and emotional context actively distort how bright or saturated an object appears. A static map cannot capture these continuous biological fluctuations. Classical physics successfully mapped the external properties of light. It did not describe the internal topology of subjective experience. The Brain Kinematics Model formalizes this internal topology through the waking equation for perceived color. In this system, wavelength distribution, W, and neural dynamics, D, establish a fluctuating sensory grid. Next, memory state coupling pulls on the grid, warping its shape. Finally, emotional loading and predictive context thread into the mesh, locking the topology into a stable configuration. The resulting color is not a single point on a graph. It is a three-dimensional, interconnected strain field held together by competing neural pressures. If the brain's internal dynamics rate is low, the sensory grid holds tight to local details. If the dynamics rate spikes, layers bleed into one another, driving heavy symbolic and emotional blending. The redness of an apple is therefore the temporary physical equilibrium of multiple, interacting cognitive layers. Because this equilibrium relies on active neural interaction, it is highly sensitive to time. We can model this temporal behavior with a differential equation, mapping out the phase space of the perceptual strain geometry as it shifts millisecond to millisecond. The critical variable here is the lambda S term, which represents dissipative degradation. Perception requires constant energy. The brain must push continuously against thermodynamic-like degradation to prevent a stable image from dissolving back into noise. If an emotional surge introduces strain that overwhelms the system's structural capacity, the bonds holding the image together fail to absorb the tension. The entire grid warps away from its physical baseline. Experiencing a clear, continuous image requires a ceaseless mechanical struggle to maintain structural coherence. Out of all possible configurations, the brain naturally settles on the most probable stable integration of these layers under the current strain. We model these highly stable states as attractor basins within a probability landscape. The neural network falls into the deepest, most efficient geometric configuration available. When sensory input is ambiguous, like looking at an optical illusion, multiple potential strain geometries form and compete for dominance. As interplay between layers accelerates, instability grows until it exceeds a critical threshold. The geometry's coherence shatters. The node dissolves, escaping its basin and rapidly plummeting into the adjacent one to stabilize a new percept. This exact mechanical phase transition explains the rapid scene shifts of REM dreaming, where a location smoothly and suddenly morphs into something entirely different. Optical illusions flipping, sudden moments of insight, and dream cuts are the same phenomenon. They are required phase transitions within the cortical strain field. If both waking and dreaming states successfully generate stable mathematical perceptual geometries, we have to ask what separates isolated sensation from true cognition. The answer lies in a functional boundary line, splitting the brain's sensory perceptual areas from its motor executive domains. This chart visualizes the cognitive transfer integral. The dynamic flow of sensory data continuously presses upward against a specific barrier, labeled theta c. Forming a visual geometry is not enough. Cognition only occurs when that sensory flow possesses enough integrated strength to physically cross the threshold and propagate into the networks responsible for logic and action. This finally resolves the paradox of the dreaming brain. REM sleep achieves high-amplitude internal sensory stabilization, yielding vivid colors and intense emotions without external light. But the transfer threshold is functionally blocked. The high-amplitude signal churns entirely within the sensory domain, cut off from executive verification. We can define consciousness as the temporary dominance of a perceptual geometry. Cognition is the physical propagation of that geometry into action. Stepping back from the differential equations, the macroscopic implications of this model stretch far beyond color perception. Waking reality, deep imagination, and intense hallucinations are built using the exact same structural mechanics. They differ only in how long their geometries stabilize and how strongly they are tethered to sensory data. Push the cross-layer dynamics high enough, and rigid physical boundaries strip away entirely. Concepts fuse and identities blend into continuous topological structures. The shapes and colors we navigate daily exist as relational equilibria, forged at the intersection of external physics and internal neural organization. This relational perspective shifts the focus from the object to the interaction. The perceived world is a compromise between external data and internal viscoelastic memory. We do not merely observe our surroundings. Our neural architecture dynamically negotiates with the universe to render the probabilistic equilibrium we call experience.